Today, we are going to talk about air brakes in heavy trucks. No, you didn't stumble on a class for truck drivers or mechanics. Explaining something about how air brakes work will help you understand how transistors work. So let's get started. So here's the deal. We have a heavy truck, so here's our 53-foot trailer with our wheels at the back. Up in the front we have a tractor that's pulling this trailer. We have our drive wheels here, our steering wheels there, an engine in there, and inside the engine compartment is an air compressor that puts air into the air tanks, and those operate the brakes. So when the driver presses on the brake pedal, what happens is it sends air from the storage tanks into some chambers. There's two chambers on each axle here, two chambers on each axle there, another two chambers on this axle, and it sends air into the chambers. I'll draw it something like this. There's a piston in the chamber that pushes a rod out of the chamber, so the air comes in here, fills this area here, pushes the piston in that direction. That piston is connected to a bell crank called a slack adjuster. So that moves that slack adjuster in this direction. Actually, when we press on the brakes, it moves it that way. That turns a shaft, which we go into the brakes themselves. We have what's called an S-cam. It's a little piece of metal shaped like an S. That turns, and as it turns, it pushes out on a couple of rollers. Gets kind of complicated, doesn't it? Those rollers push out on the brake shoes, which are inside the brake drum, and those brake shoes are pushed out against the brake drum, and that stops the truck. So that's the basics of how the air brakes work. The problem is right here, because these brake chambers on these axles are fairly close to the air source, but to get the air to these, you have to go through a long, narrow hose. And the problem is, it's just like a long, narrow wire. It has a lot of resistance. And these air chambers act like what? They act like capacitors. And so a lot of resistance and big capacitors, it's going to take a while for that air to go down that hose and fill those chambers and make them operate. So basically, our front brakes are going to lock up before the rear brakes on the trailer even start working. Truckers consider that bad luck. So what can we do? Well, the solution to this is that while the truck is rolling, so to start the truck moving, before you can put it in gear and press on the accelerator, you need to release the brakes. And to do that, you press a big button on the dash, and that causes air to fill up another air tank back here. So whenever the truck is rolling, there is air in a tank back here. But now we need to get the air to those chambers. So here's that tank. It has a big hose that goes to a valve. And that valve has other hoses that go to the other four chambers. I'll just show them as two chambers here. And the hose goes to that valve. And what happens, if I can try to draw that a little bigger, let's get the truck out of the way here. So here's the body of that valve, and inside there's a spool or other mechanism. There's going to be a spring back here. And so this is shown as two separate pieces, and I'll just kind of show that these have some substance in there. And we have an air hose coming in about here, and another one going out about there, and then the little hose coming in here. So what we need to do is push this spool or piston, whatever you want to call it, backwards so that it compresses the spring. Try to redraw this here. Moves everything back. So now there's an opening between here, and air can go through that. So a little bit of air pushes that piston back, or the spool back, whatever you want to call it, opens up this airway and allows air to go through here, which splits off to those two chambers and operates the brakes. And now a little bit of air opens the valve, takes a lot of air from the tank here to quickly open those brakes, and so the brakes at the rear of the trailer operate in unison with the brakes of the rest of the truck. So why did I tell you all this? Because this valve, called the relay valve, is a pneumatic transistor. That's exactly what a transistor does. Let's relate this to a bipolar junction transistor. So I will draw the schematic symbol for that right here. And so we're going to have probably a resistor here for current limiting or other purposes. And here's a battery over here, or some kind of a voltage source. Drawing a common emitter circuit here. We'll talk about those way down the road in analog circuits. And so this battery is representing that air tank that's at the back of the trailer. And this connection here at the base of the transistor, so this is called the collector, that's called the base, that's called the emitter. So right now this transistor is acting like a closed switch, it's acting like the closed valve. But if we put a little bit of current into the base, it's going to cause a lot of current to flow from the collector to the emitter from this source here. So we have a different source over here. More about that when we talk about amplifiers. But there's a voltage source here that ultimately gives us some voltage at the base. There's some circuitry that controls things, that turns the transistor on when we want it on. So a little bit of current in the base causes a lot of current from the collector to the emitter. So it's like that relay valve on the truck. So a little bit of air opens that valve and causes a lot of air from the rear tank to go through to the brake chambers. This, a little bit of current into the base, causes a lot of current from the collector to the emitter. Now, to look a little deeper into how a transistor works, we are going to look at the little green man model. Now, the LGM model of how a transistor works. This is based on a model called the hybrid parameter model. I'm not going to get into that other than to say this is where some of the names come from for the parameters I'll talk about. This resembles it, except we have a little green man who's controlling things. So the little green man model starts out, we have a current meter, and over here we have a variable resistor and another current meter. So this is our base, this is our collector, and everything's connected here at the emitter, which we will send to ground. So once again, it's a common emitter amplifier. Again, we'll talk about those down the road. And controlling everything is a little green man. Now he's got his head on a swivel. That's his nose. Watching this meter, and then he turns around and looks at that meter. So he's constantly watching those meters, and he has his hand on that variable resistor. And he has an instruction card inside his little transistor that is labeled HFE. And then there's a number. We'll make that number 10. So that's the HFE of the transistor. And this comes from that hybrid model. H stands for hybrid model, forward current, common emitter configuration. That's where this comes from. There are other H parameters, but this is the only one we're going to talk about. And the hybrid model kind of resembles this, but it's a little more technical and less fun to talk about, and really not necessary to get deep into, but this will show what the transistor does. It's a little smart circuit, and in this case we're controlling it with this little green man, whose instructions are to make sure that the current from the collector to the emitter is equal to, see, that's going to be our current through the collector. His job is to make sure this current is HFE times this current. In other words, we have a current going into the base. Let's say that current is 1 milliamp. His job is to make sure that the collector current is 10 milliamps, or 10 times, or HFE times that. So his little formula is IC equals HFE IB. A little bit of transistor math there. So that's his simple job. So if we put in, once again, 1 milliamp, he adjusts this resistance until he sees 10 milliamps on that meter. If we increase this to 2 milliamps, well, he's going to have to decrease this resistance until we see 20 milliamps over here. And that's his job. Now, they're not perfect. The exact ratio depends on certain parameters, and our HFE will change depending on temperature and voltage and base current and collector current. It can get a little complicated from an engineering viewpoint, but for the main part, it's that simple. Different transistors have different HFEs. I've seen them up to 100. For power transistors, 10 is kind of typical. And that's basically all a transistor does. Now, field effect transistors are a little different in that they say they're voltage controlled. Let's draw a simple junction field effect transistor here. And in the case of the field effect transistor, we have the same thing. Let's draw our voltage source over here, going from the drain to the source. So instead of base, collector, and emitter, we have the gate, the drain, and the source, different names, but they have the equivalent purposes. And this time it's voltage that controls it. And I want to make a point here because, of course, if we change the voltage at the base of a bipolar junction transistor, it changes the current. But when we look at the current, the collector current has a linear relationship to the base current, but the collector current has a logarithmic relationship to the base voltage. So we say that a bipolar junction transistor is current controlled because our relationship is linear, not logarithmic. It doesn't mean that changes in voltage don't change the bipolar junction transistor. It's a matter of relationships. In this case, the drain to source current, that's going to be IDS, is linearly proportional to the gate to source voltage. So we have VGS, the gate to source voltage, and a linear relationship between that and the drain to source current. And if we wanted to make this a little green man model, let's take a look at how that would look. In this case, because in the case of the junction field effect transistor, or the junction FET, the junction between the gate and the rest of the FET is reverse biased, so it kind of looks like a capacitor. So we're not going to get any current through there. And so we just have a voltmeter here. And this is going to have the, once again, this is going to be the gate. This is called the source. And so this would be called a common source amplifier instead of a common emitter amplifier. And over here we're back to what a bipolar junction transistor looks like. And once again we have our little green man watching those meters and controlling this variable resistor. With the field effect transistor, the equivalent of HFE is called the transconductance, represented by a little g and a little m. And so he's going to be looking for a certain voltage here and then adjusting the resistor to get a certain current over here. I'm not going to say much more about field effect transistors because I'm going to have a whole video dedicated just to them. One other thing worth saying, although we don't see this too often, I'm going to explain the characteristic curve of a transistor. So here is our voltage versus current, and we have two things going on here, so I'll have to kind of have more than one scale, but it'll become clear once I get going. Let's make this 10 volts, and I'm going to make this voltage from the collector to the emitter. So a quick drawing of the circuit. Here is our bipolar junction transistor. Once again, a common emitter circuit. And what we have is a variable battery, 0 to 10 volts. And that controls this voltage from here to here, which is the VCE, voltage from the collector to the emitter. And then we're going to have different base currents. So I'm going to have another battery here that's variable. And I'm going to put a current meter here because we're interested in the base current. And so we're going to put different amounts of base current and then vary the voltage here to get different VCEs and see how the transistor operates. So let's get this out of the way to make the graph. And let's say we have no base current. So this is going to be the collector current. Forgot to put that there. We have no base current, and now we're going to increase the VCE. And what we find out is that we get just a little bitty tiny bit of collector current. So this is the curve we get if our base current, IB, equals 0. Let's make that 0 just a little bigger there. So base current equals 0. As we increase the voltage from the collector to the emitter, we get just a little bit. Notice that this is flat, so we increase the voltage, we don't get much of a change in current. It's a very slight slope. And a silicon transistor has a very flat slope. But now what we're going to do is increase our base to emitter current. So let's increase that to, well, this is arbitrary and relative, let's increase it to 1 milliamp. So now we've increased the base to emitter current to 1 milliamp, and we're going to see that this goes up. Once again, fairly flat, and this curve happens when our base current is equal to 1 milliamp. And let's say we have an HFE of 10, so that's going to be roughly 10 milliamps over here. So notice it's very flat. As we change the collector to emitter voltage, we get almost no change in our collector current. The collector current is dependent on the base to emitter current, or the base current, which is here. Now let's double that to 2 milliamps, and this should be just about twice as much. Our base current equals 2 milliamps, and that means that's going to be roughly around 20 milliamps. And so each time we increase our base current, notice we get a little area here where it takes a little longer. In fact, this is following the voltage of the forward bias diode that makes up the base to emitter junction. And so this is going to be roughly 0.7 volts around here, so we get that curve here. And as we increase our base current and then vary our collector to emitter voltage, we get this peels off at different levels. And we get a curve that looks like this. So 3 milliamps, 4 milliamps, 5 milliamps, and increases up to 30, 40, and 50 milliamps on the collector current. So that's the basic understanding of that characteristic curve that you might see here and there. There are some things we can do with this to design amplifiers, but we're not going to talk about that today. We'll talk about that when we talk about amplifiers. So that's basically how that curve works. And for what it's worth, let's see what this looks like with a field effect transistor. With a field effect transistor, we don't get quite as flat a characteristic. With 0 volts from our gate to our source, we're going to get something like that. I could draw that a little better. It's going to go up a little more rapidly and then heel over. We increase our gate to source voltage and then play with our drain to source voltage. We're going to get something that goes up a little more like that. We increase our gate voltage. It's going to go more like that. Notice that it's getting more slopey each time I do this. Increase the voltage, we get something more like that. And so our characteristic of our field effect transistor is not as clean as the bipolar junction transistor. And another interesting thing is, notice in this region here, I'll draw a little circle around it. Notice these are fairly straight lines, and as we increase our gate voltage, it changes the angle, which would be exactly what we get if we have a variable resistor. As we change that resistance, we're going to get a straight line, but at steeper and steeper angles. And so in this region right around here, our transistor is acting like a voltage-controlled variable resistor. But then we get over into this region over here, it acts more like a transistor, where changing the gate voltage causes a certain drain to source current based on our different gate to source voltages here cause different amounts of current. So it's more like the bipolar junction transistor. So there is the variable resistor mode, and here is the amplifier mode over here. That's the characteristics of your field effect transistor. So that's about all I want to say about transistors at this point. I'm going to have more videos about field effect transistors and about amplifiers, and more about this when I talk about amplifiers. But that's the basics. So what is a transistor? It is a either current or voltage controlled variable resistor or switch, depending on how you're talking about it. Some small transistors that can turn on and off very fast are referred to as switching transistors. So if I have a transistor and if I put a lot of current through it, it's going to turn it on and have a lot of current. So it's going to be like a closed switch, but if I take that current away, I get no current here, and so it's like an open switch. So transistors that are optimized to work that way are called switching transistors. And other transistors like power transistors are of course made to handle a lot of current, and they're bigger and able to be put on big heat sinks. But the main idea is we have a current through here, a little bit of current, make a little dashed line here, a little bit of current from the base of the emitter causes a lot of current from the collector to the emitter. And so it acts like a current controlled variable resistor as I showed, or if we go back to the truck to understand the basics of how it works like that relay valve where a little bit of air opens the valve and where a little bit of air opens the valve and causes a lot of air to go from the collector to the so a little bit of air opens the valve and causes a lot of air to go from the air tank to the brake train. So a little bit of air in the valve causes a lot of air to go from the tank to the chambers at the rear of the trailer. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe and hit that gray bell also, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.